Here's a question. What's the difference between a series and a sequence?
A series is an addition of sequences.
Oh, that's nice. Yeah. So sequence are just AN, and then series is the sum of sequences, right? Series is the summation. And we've been talking about many examples of series that converge and series that diverge. And when I go through this, often it's a point of confusion whether I'm talking about the limit of a sequence or the limit of a series. Okay. Yeah. So to get a good example for a discussion, can you give me an example? It could be something that we've already done. Example. Give me an example of a series that converges.
1 plus 1. Right?
No, infinite series.
Oh.
Okay, yeah. Things that you add infinitely many of, but you get a finite number. Give me such an example.
1 over 2 factorial plus 1 over minus 1 over 4 factorial.
Okay, well, so you're saying 1 minus 1 over 2 factorial plus 1 over 4 factorial plus 1 over. Oh, that's just too complicated. Can you get something easier? Yeah, I agree. This converges.
4 over x. 4 over x.
No x's. I want numbers.
1 plus 1/2 plus 1/4. 4.
Plus
1/8.
1/8. Okay, I like that. Okay. So by the way, we learned that this one is cosine of 1. And this one is an infinite geometric series with, we have to use a over 1 minus r as the formula for the infinite geometric series. And the first term is 1. And the common ratio is 1/2. So this will converge to 2. Okay. So let's talk about this one. So summation of n equals to 0 to infinity of 1/2 to the nth power. That's this series. And I want to talk about the limit of the series and limit of the sequence. So when I say limit of the series, I mean the entire sum, right? What's the limit of series again? The summation is? Summation is? 2. I just wrote it, right? 2. If you add them up, you get 2, okay? What's the limit of the sequence? And what do I mean by when I say sequence? What's the limit of the sequence?
Infinity.
Yeah, what's the an here?
The 1 over 2.
1 over 2 to the n.
Yeah.
Okay, 1 over 2 to the n. What's the limit of that?
0.
0, yeah. Limit of the sequence, 1/2 to the nth power, as n goes to infinity, that's 0. The infinite series is 2, and individual terms that you're adding gives you 0. Okay? And one of the things that I was talking about in the last class was how it's necessary for the limit of the sequence to become 0 if your original series converges, right? Because imagine that you're adding something. So you have, I was talking about these things as jumps, right? So you take plus 1 as a jump, and then half step and a quarter step. You keep adding. And if you have any hope that this is going to converge to some number, then your step sizes should be what?
Getting smaller.
Getting smaller to 0, right? So that was what we were talking about. So we talked about the test for divergence, also known as the nth term test, as the following statement, that if the summation is to converge, if you get some finite value, or let me just say converges, then the limit of the sequence is what?
0.
0. It has to be 0. Okay. And then I talked about the fact that the converse of this doesn't hold. What's a converse? You take a statement, a proposition has an assumption and a conclusion, right? If you switch those two, that's called a converse, right? So what's the converse of this statement?
If the limit,
If limit of n going to infinity of an gives you 0, then summation would converge, right? Now I put this in quotes because that's not true actually, right? Yeah. And it's a bit counterintuitive because you think like if you're going always to the right and your step sizes are getting smaller and smaller, wouldn't you at some point just arrive at get close to something? How can it still go to infinity? That doesn't really make sense to you. But surprisingly, I gave you two examples. One example was ln of n plus 1 over n, or was it n over n plus 1? N from 1 through infinity. And the other example was summation n equals to 1 through infinity, 1 over square root of n, square root of n plus 1. Both were telescoping series, and I showed that these both give you infinity. Whereas this one, to quickly explain how I did it, was I multiplied the conjugate top and bottom, right? And the result is that this turns into like summation of negative square root of n plus square root of n plus 1. So that if you write it, it's like negative square root of 1 plus square root of 2 plus negative square root of 2 plus square root of 3, da da da. And by the way, this infinite sum is thought to be the limit of the partial sum, so you end at negative square root of capital N plus square root of capital N plus 1. And because everything in between will just cancel away, and you just have the very first one, negative 1 and plus square root of n plus 1, and this becomes infinity, this limit goes to infinity. So that was like the quick calculation I did at the end. But like how you get it is not the point. Just look at this result. It seems so counterintuitive. That what's the limit of sequence here? What's the limit of the sequence here?
the limit of
Negative
that.
1.
Yeah.
What's the limit of the sequence? Not the limit of the series. What's the limit of the sequence?
1.
And so you'll have
Without the sum. What? I'm just talking about this one. What's the limit of this thing?
You'll have square root of infinity plus square root of infinity plus 1. So
Under
1,
1. So it would be 1 over?
it would be 1 over infinity, which is 0.
Which is 0, yeah. So the limit of the sequence will be 0. So when n is really, really big, you're practically adding zeros. Yet, what we just saw is that the sum still managed to go to infinity. So I like to use the terminology that this series is crawling to infinity. So Can you picture that? You're moving to the right, and every time you move right, your step size is getting smaller and smaller, so that when it's really, really far out, you're basically crawling to infinity, yet somehow it manages to go to infinity. It's strange how that can happen, right? So to help you with this idea that how you can actually crawl to infinity, let me draw you a picture that's going to give you an idea of what I mean. So here's an example that we did in improper integrals. So integral from 1 through infinity of 1 over x dx. The meaning of that integral is, first draw the graph of y equals to 1 over x. And this is the area under the curve from 1 through infinity, right? Now we know from improper integrals that sometimes this integral gives you a finite value, but not this case. If we actually do the integral, what's the integral of 1 over x? ln of x. We plug in infinity and 1. We get ln of infinity minus ln of 1. What's ln of 1?
0.
So that's gone, and you just have ln of infinity. What's that?
Infinity.
Infinity. So this area under the curve is infinity. And then once you accept that, think about the following picture. Just divide this infinite area from 1 to 2, 2 to 3, 3 to 4, 4 to 5, and you think of these individual areas. And think of these as the sequences. The sum of all these sequences will give you infinity, right? You agree? Because that's the entire area. But what's the limit of individual sequence here? The individual sequences themselves go to what?
0.
0. The thing that you're adding becomes 0. Yet it manages to go to infinity. Right? So the moment you accept that this picture is an infinite area, you have an example as a picture where your thing that you're adding is getting smaller and smaller, yet this adds to infinity. Yeah, you can actually do the computation from n to n plus 1 of 1 over x dx to get that this is ln of n plus 1 over n. So actually this series that we talked about last time calculates this area. And this one, we know that it goes to infinity, for the same reason. So instead of using telescoping series, which I did to prove that this is infinity, I could have used that picture to say, hey, this represents this, and we know that this integral is infinity, so the sum is infinity. That could have been another way to do it. Okay. Now, the simplest case where you have a series that's crawling to infinity is the following one. 1 plus 1/2 plus 1/3 plus 1/4. This series here, we're going to prove that this is infinity. But that's really counterintuitive, don't you think? Before I show you that this goes to infinity, I want you to understand that sometimes the question of whether it does converge or not becomes a very crucial question because, for example, let's say you are working as an engineer and somebody did some computation that involves some complex integrals and all that and came up with the answer as this one. And then he says, okay, can you just write a program to calculate the approximate value of this? because I can't find the answer in closed form. Right? And so as an engineer of the company, you would take this and you write a Python program, a MATLAB program, add, say, 1 million digits, right? 1 million of these terms, and you get some approximate value. Right? And you even do like million, million, 1 million a second, and then you see that the thing does increase because you're adding more terms, but then it's not increasing as fast, because if you're adding 1 over 1 million, that only changes the 6 digits. So once you start adding 1 million and 1 million and 2, then the summation becomes quite stable. So you look at the series and see how it's not increasing by that much. You stop the program and report back, okay, so I added 1 million terms. Here's what I think is the approximate value. You give back the result, and then the moment you claim that, what you've done is that you've estimated the value in a very wrong way. In fact, what will be the error? If this is actually infinity and you gave them a finite number, what will be the error? Infinity. Yeah. You've estimated infinity as some finite value, so it's like grossly wrong. You don't want that, right? So that's what's going to happen. On the other hand, if you had 1 plus 1 over 2 squared plus 1 over 3 squared, we're going to prove in a moment that this actually converges. So this will be infinity, but this will be some finite number. We'll be proving that. Okay? So let's say you did the wrong thing and you got scolded, like, oh, that's like grossly wrong, right? And then that coworker gave you another assignment. Okay, give me the approximate value for this one. Now you again calculate 1 million terms using your Python program or MATLAB, and now you want to say that the approximate value for this is something something, but this time you're very unsure, right? Because what if you add billion or trillion terms, this will give you some much bigger number. What if that happens, right? So that's actually a big issue when it comes to approximating the value. Now, of course, you would say, well, if we know the actual value, why bother approximating it, right? Because for some series we did know, right? So here's a surprise. For some series, we do know the answer in closed form. So we do know that this is pi squared over 6. But if you add cubed, this does converge, but we don't know its value. In fact, this one has a name, zeta of 3. If you can find the answer to this, not approximate value, but the exact value, just like this form, right? Maybe it's like pi cubed times some rational. That's what a lot of people think, some fraction times pi cubed. Or maybe it has a natural number e or something. If you can write in any form that's exactly right, then you could become famous. Just knowing this value. You could be on the news. Like a mathematician finds the value of 1 over cubes. Then here's another interesting fact. If you do 1 plus 1 over 2 to the 4th, 3 to the 4th, 4 to the 4th, then we do know the value. This is pi to the 4th of 90. Yeah.
How did we know the exact value?
The exact values for these, actually, I don't know off the top of my head. It's very hard. You need to do some Fourier series, something. It's not easy.
Oh.
Yeah. But just like we had pi over 4 last time with the Gregory series, right? And the way you get it was like, there wasn't a standard way to do it. We just happened to find some function as sum of some power series, and you were able to plug something in, right? So there's another series called Fourier series, which is also an infinite series, and you can evaluate Fourier series at some special points to also get something like this. And then when you change this to 5, the zeta 5, guess what? Guess what?
Becomes 1.
No, we don't know the value first. Well, it's always bigger than 1 because it's 1 plus something, right? Yeah. It gets closer and closer to 1, but the thing is, every time it's odd, we don't know the value, and every time it's even, there's a closed form formula for it. So what that suggests is like, oh, there's no hope for us that we can figure out the actual value of a closed, actual value of an infinite series. So if that's not possible, then the big question for a series would be that does it converge? Especially for an engineer, that would be true, right? Because for an engineer, who cares if it's pi squared over 6 or some other value? You just need the approximate value for your next computation, right? So the most important question, so I'll just say big question for series is, does it converge? Or does it diverge? If you can answer this, then you can confidently estimate it using some program. Or you can see that it diverges, so you don't even bother computing it. Okay? So that's the important thing. And actually, we've made some progress to this question because we now know a few things about it. So what we know so far. So number 1, if limit of the sequence goes to infinity, does not go to, if, sorry, number 1, if limit of the sequence goes to something other than 0, or if it completely diverges, then what happens to the series? What happens to the series? Diverges. That's the test for divergence. If this ever happens, then no question, it just diverges. So we don't even bother computing the approximate value. If limit n going to infinity of an is equal to 0, then what do we know?
It converges.
Oh, goes to infinity.
Then the series.
No, the series sometimes converges and sometimes diverges. That's what these are doing, right? This one diverges, this one converges.
Then it might converge.
It may converge, okay? Yeah. May, so then it may or may not converge. So basically we don't know anything. However, if sigma an is so what do you call that series where you have plus and minus repeating, alternating?
The geometric?
No? Plus.
Telescope.
Huh? No. Plus minus alternating. Alternating series.
Oh.
Alright. So if it's an alternating series, we actually had 2 criteria for it, right? It requires 2 things. And number 1, limit of the sequence does go to 0. Number 2, the next term is always less or equal to the previous one, we put absolute values because the signs change, then it converges. And we actually have an error estimate in this case, right? If you truncate at some point, then the next term gives you the error of the truncation. So we talked about that when we did that. And the picture for that was like you're jumping back and forth, back and forth, back and forth, and whatever that's jumping, let's say it's a frog, it's losing energy as it's jumping. So gradually it would be converging to some value. Okay? That's what happens if you're jumping back and forth when you have an alternating series. But other than that, we don't know what happens if the limit of the sequence goes to 0. Okay, so convergence of these types will be discussed later, but let me just say a little bit more. So from this point on, what we're trying to do is to expand this result. So it'll be like item D, E, F, G, and so on, where we add additional facts about it. If it does this, then it converges. If it does that, it diverges, and so on and so on. So what we have is basically a bunch of different tests. Just like if you're sick and the doctor doesn't know what your sickness is, you're sent to the lab and you have to take blood out, you get blood samples, and they do all kinds of tests to see what's wrong with you, right? And sometimes those tests don't come out to give you a clear conclusion, and you have to go through further tests. Just like that, we're just developing more and more tests. In fact, the test that we come out with wouldn't be complete because there's still some series out there that we don't know if it converges or not. So, for example, mathematicians are still trying to figure out if this series converges or not. We don't know if this converges or not. And the thing is, if an integer is a multiple of pi, well, it's never a multiple of pi because pi is irrational, right? But if this integer is very close to a multiple of pi, then sine of pi is 0, so you get a very small denominator. And that makes this thing kind of spike up anytime that happens. So that's why it's really hard. So right now, there's nobody on this earth that knows whether this converges or diverges, although people think it will converge, but there's no proof. People are still writing papers about it. So, yeah, but we'll just be doing easier questions than this. But I'm just trying to warn you that the question about convergence of a series is not that easy. You have to pick a test, and you have to learn new tests, and some of them might not give you a conclusion.